subnets. The subnets correspond to different type of small networks within the branch. For example, one could be the teller network, other could be the manager's network, then the Wi-Fi network. All these form different subnets. And then they connect through some hardware switches, and finally there would be a customer edge router, which will talk directly to the private cloud. So that is how it traditionally it looks like. In the SDWAN world, what happens is we replace the customer edge routers using SDWAN virtual gateways. So what that basically means is like it is a off-the-shelf hardware, commodity hardware, which will have a few access ports and a number of uplink ports for talking to either the internet or on the WAN side, and it will have customized Linux-based ways, which could be Red Hat or Ubuntu or something, and then of course at the heart of it will be open vSwitch enabled data path. So this is how it architecturally looks like from a very high level. You will have these machines configured as different subnets, and then each subnet will be represented by virtual ports on the open vSwitch, and obviously they are VLANs, and they will be talking through one or more hardware switch. So this, up to this, I have laid the background of what we will be talking about next. So what are the problems we are looking at here? So the problems could be something like what happens if the access links fail. So it could be like the physical link itself failed, as is shown on the leftmost side, and then in the center I have shown that one of the ports in the virtual gateway has failed. Or on the other side, if it could be the hardware switch port which talks to the virtual gateway, that also could fail. So either way, your branch machines will be partitioned from rest of the network, which is not a good thing. What happens if the uplinks fail? Like one or more uplinks could fail, and that could create problems. Like you will not be able to reach the rest of the network. And then the other use case could be the SVG itself, the virtual gateway itself could crash, or even the virtual switch might fail for some reason. So in all these cases, we need a way to build a fault tolerant and a reliable gateway, virtual gateway, and we will see how we can do that. So I will spend a few minutes on the proposed solution at a higher level, and then we will go deep depending on the time we have. So what we are suggesting here is that we deploy the solution, deploy the virtual gateways in active and backup mode. So what that means is, like, we will form a VPLS kind of connection with the access ports, one each from the active and the backup gateway, and then we will give it for each subnet. So what that means is, like, your traffic coming from machine M1 or M2 will be given to the active gateway and the backup gateway, and we will figure out a way how we can make sure that the traffic actually drops or finally doesn't reach into the network. So this is how the physical view of the solution looks like. So as I said, like we will configure the master, one SVG as a master, as active, and then the other as a backup. And then we could potentially choose to configure each of the access ports in either active or backup mode. There will be different use cases for that as well. So one of the great things about OVS is, like, it provides a lot of services through which you can build your application. So you have a very good implementation of RFC 5880, which is the BFD, bidirectional link forwarding decision protocol. It is already implemented, and it supports full very good link monitoring services. What is not there yet is the liveliness of the link, and what is not there yet is the mastership of the link. So what we mean by that is which gateway is master. It is right now not there, and we will see how we have enhanced it to implement that. Here, in this slide, I have put the BFD packet structure. So here, of interest are the two fields like my discriminator and the your discriminator fields. So these are primarily non-zero random values which you add so that you can identify which node the packet really came from. An example will actually make it very clear. So as we see, node number 1 on the left starts with a my discriminator value of 1, 2, 3, 4, and the node number 2 on the right has 5, 6, 7, 8. And then what they do is they start exchanging the data in steady state. Both of them will have the desired values. So by looking at the packet, you will know from where it is coming, which node is sending. And each time a packet is received, what OVS does is it will reset the detect timer. So basically meaning that all is well until this point. And what happens when there is a failure? So let's look at this. Like node number 1 sends the packet, link hello packet, and then it is sent for 3 times, as is shown by the detect multiplier. And after 3 times, when there is no response on the other side, it will say that the timer has expired and it is time to actually notify the clients. So what we do, what we have done to extend this solution is we have reused the my discriminator and your discriminator fields to contain something called the mastership role. So 1 indicates it is master and 2 indicates it is backup, and also we send the upper 16 bits to give the openflow port number itself, so that on the other side we know which port has actually failed. So let's take a look at how this will work in the in this mastership case. So first, when we start on the left-hand side, we have the backup SVG starting with a roll of 2, and on the right-hand side, the master SVG will get a roll of 1, and in steady state, they have the roles exchanged. Now, when there is a failure, on the backup side, we see that after 3 non-receives of the packet, we will see that it has not gotten it, and at the end, you will see that the my discriminator value is changed from 1 to 2. So basically, that means that the backup SVG has assumed mastership of the particular link. So with about 400 lines of code change in libbfd of OVS, we were able to implement the heartbeat negotiation and mastership. So whatever we modified is listed here. Primarily, we get the configuration through openflow commands of which port is the master, and we could also do it through OVSDB. And finally, we get into the packet path, which is BFD process packet. And with Linux, NetDev Linux run, we monitored the uplinks and then also made sure that this status is also reflected in BFD for mastership. So this was the heart of the solution, whatever we did. Now we will see how we apply it to SDWAN. So we create one additional extra bridge, which we call the vSwitch Resiliency Bridge. So this is primarily to keep the customer traffic and the data traffic, customer traffic and the control traffic separate. So what we have here is if you see here, the ports on the resiliency bridge are using the VLAN 4094. So for each of the ports, access ports, you will have one port in the resiliency bridge, and they are color coded in red, and then they will form the VPLS connection as we discussed earlier. So what are the challenges here? So as we discussed that you will see, because of the VPLS connection, you will see that the backup SVG will get the packet. So we need a custom rule that as soon as a port is configured as a backup, we will automatically drop the packet. So we create a rule like that, and so that takes care of the duplicate packets. So the next interesting part is the gateway statefulness. So what that means is, like, each gateway in SD-WAN, SVG, will implement certain networking functionality as well. Like, for example, the DHCP. So whenever a branch, in a branch, different machines come up, boot up, they will ask for IP addresses, and they will send out DHCP requests. So one implementation could be that the SVG implements some sort of a DHCP server, which gives out IP addresses for any of the machines that come up in the branch in the same subnet. So what really needs to happen in this case is, speaking at a broader sense, that we need to have a sense of state replication for each of the services that the SVG provides. So what we need here is actually a bidirectional state synchronization. It could so happen that some of the ports in the configured backup SVG could be really operating as a master, and some of the ports could be configured as a in the master is actually operating as backup. So we need bidirectional state synchronization. So let's take a look how this can be done. So in this diagram, what we show here is we created a new daemon called the SVG sync D. So that daemon will be using usual TCP/IP links to TCP/IP methods to actually synchronize the state offline, and it has to be very much up to date, keeping both the SVGs up to date. Then you have the data path daemon in the middle, data path bridge in the middle, which is like this one, and then there is the resiliency bridge, which exchanges the heartbeat information shown in the red lines there. Another potential issue could be how to avoid Splitbrain scenario. So what could be like what if the downstream switch itself goes bad, and all the ports in the downstream switch goes bad, and both the SVGs come up as master, and they advertise the routes to the controller, and that brings about very bad things. So how it can be solved is by using BFD on the management interface as well, or we could even ask the customer to have a redundancy on the downstream switch. So that solves the Splitbrain. So how this actually works, so another quick look at how this is supposed to work. So you will have a config coming down from the controller, and you will configure the port level BFD on the virtual switch, and then you will also kick off the state synchronization daemon. So it keeps synchronizing state in the background, and the BFD link failure happens here, and as soon as that happens, the virtual switch sends a notification to the clients, which in this case is the SVG sync D, and he takes over the responsibility of syncing state in the other direction now. So this is how it will work. In SD-WAN, how do we intend to implement? How did we implement this? Is basically you have to configure the resiliency information of the gateways through the CMS. So with OpenStack Neutron plugin, you will give the configuration to the openflow controller, and from the openflow controller, the configuration will come into the SD-WAN SVGs itself, and then they start exchanging the BFDs between themselves. So whenever there is data that has to be sent, so either one of them, not both, will send the data out to the data center, and it will be through that. And yeah. So we are at the end of the presentation, I guess. Like, we demonstrated how we extended RFC 5880 to do mastership, and we also built the state synchronization, statefulness synchronization. The work was started in 2015, and we productized it in Nuage Networks Virtual Networking Services product in 2016. Obviously, I want to thank some of my teammates who helped model and implement and test the solution. Future work, we intend to give the BFD mastership resolution work to upstream. We believe it will add to value for people who are implementing similar kind of gateways. And we do have future room for work with the state synchronization as well. Say, for example, we could use the OVSDB bidirectional OVSDB replication, which is there in 2.6. And then if we want to sync something outside OVSDB, then we need something like etcd. So we are looking into that as well. I guess I'm at the almost at the end. I have a few references and questions.